I feel like what's about to go wrong is going to be really obvious in about 30 seconds. So we've been screwing around. Let me show you our third grade science project. So this drill is attached to an all-thread screw that we're going to turn, and we are going to move this component of it in order to break this paracord. This is a linear actuator if cavemen made linear actuators. Now, it is free spinning in here just because we just have enough force keeping it inside of there when we are pulling our samples. The nut here is long and is stuck in the wood, so that nut can't spin, forcing this to move. This plate is here so the nut doesn't get sucked through the wood, and this is free spinning through here. Now this should move up and down, allowing us to break a sample. This has 0 data acquisition, meaning there's no load cell anywhere in here to tell us the data, but it is fun to see things break. Now the mechanical advantage I have is the screw itself. I guess you can consider what's going on in the drill that, but there's no gears here. It's a 1-to-1 in the screw. Somebody can do the math on this for us if they want. I should get safety glasses because I am staring straight down the pipe of this thing. I feel like what's about to go wrong is going to be really obvious in about 30 seconds. I'm scared. Oh! Did we break the right thing? And the wood. We broke the wood. That was X kilonewtons because there's no data acquisition on this guy. Turn a screw to break things. Should we size this up a little bit? This is a WTM, a wood testing machine. Let me give you a tour. This is our rub tester, and we have a wheel here, a drum, so we can move a rope back and forth. And in this case, we were testing abrasion on products. You can see here, we don't have a motor anymore because we recycled the motor into this prototype of a design that I'm curious about if it'll work better for us. This is a servo motor, which means it's a smart motor and it knows where it's at and it corrects itself if it's not in the right spot. And then we have a gearbox, and this is a 25-to-1 gearbox sitting on top of the motor, which turns this bar. And this bar turns this wheel. Now we have 48 teeth on this wheel and 30 teeth on each of these wheels that are mounted to these ball screws. Now this angle iron is fixed here, and this mount is going to hold this screw in place while it spins. And then we have a ball nut. Now a ball nut is a nut that moves up and down, and it has ball bearings that is rotating inside of this pitch here of this screw. Now this is an Amazon screw that was cheap and is intended typically for hobbyist CNCs or 3D printers. This is not rated for what I'm about to do with it. Now this is mounted to another piece of angle iron that you'll see going up and down. And this has a ring attached to it with our fixture here. It wouldn't be a wood UTM without a wood controller. So that's the on button, and that'll lower it, which is probably the most dangerous part, is this spinning without anything covering it. Safety is on the list. It's just not first on the list. So you can see here that moves up and down. And on this tester, we do have a load cell mounted at the top so it doesn't go flying when things break, and it's held strategically with paracord. Now this UTM is basically inverse of what you would typically see on the market, because most of the time they're going to pull up and then the sample doesn't go flying as much. But what happens is if you have a 2-foot screw, you have 2 foot of throw. That means 2 foot, period. So if you want to put a 1-foot sample in there, you can only pull it 1 more foot, metric foot, of course. So let's say a 6 metric foot span set and only need to pull it 1 foot. Therefore, I don't need a 7-foot screw. 7-foot screw that's strong enough to pull a span set is going to be expensive. But if I put a 2-foot sling in here, I want to be able to pull probably about 6 inches in order to get this thing to get all the slack out of the system. And then it starts pulling to failure. Hopefully the sling fails. You need another 6 inches for that. And then something goes snap. Well, I only have 2 feet of throw. That's why this is backwards. And that's why another thing I wanted is to be able to disassemble this so I can hypothetically put it in a van, travel around and take it to trade shows and break stuff live. Just thinking out loud here. but I need to be able to take it apart. Shall we break some paracord? Let's repeat our last test and find out how strong this paracord is. Now, if I don't want to put in a long sample, I can just use an extender of something of the sort. So we have slow and we have rabbit mode. It's working. That's pretty cool. 550 pounds is 2 kN minus, oh, hey. That's pretty cool considering this is made out of wood. Oh wow, it broke in the knot. 1.5 kilonewtons. Now this is a belt drive, or it has a belt that's driving the screws, but another way to do it is dual motor, where each screw has its own motor and requires them to be smart enough to not have one go faster than the other. We just happen to have a motor. This is why we did the way we did it. Let's pull something stronger and see where the weak spots are on this. Now, loop of cord in theory is twice as strong, but I typically only get 180% out of it. This is cool. Wow, it broke in the knot. How's my math? 2.91 kilonewtons? Yeah, almost double. So to reset this, I just reverse in rabbit mode. Cyclic loading is actually very interesting, which would allow us to do more detailed science. A loop doubled, in theory, would get you double-double. We'll find out what you really get. We just took a wood testing machine up to 6 kilonewtons. What was the snapping sound?
Some settling may occur.
Now I'm curious how strong the wood is, because I don't know about you, but my house is made out of wood and it looks heavy. If we can get up to 30, 40 kilonewtons, we are gonna jump straight to a Dyneema sling, and we're gonna find out if something breaks on this machine, because these are gonna break around 26 kilonewtons, maybe 22 is what it's rated for. It's an old one, maybe 18. Either way, I'm not expecting this to survive, but I would like to survive. So I'm gonna hopefully stand behind something. I wanna look so bad. I know not to.
8.7 and it's stopped. No.
Oh, the wheel fell off. Oh no! That is 10 kilonewtons. I mean, we got 10 kilonewtons there. That's the controller, by the way. So that wheel, I think, is supposed to be attached to that. How did that thing fall off? That, I guess, has a lot of force being put on it. Notice how slowly this pulled. My machine pulls at about 1,400 millimeters per minute. Many machines, or even testing standards, is only 100 millimeters per second. I'm pulling 14 times faster than most tests. And so Dyneema is going to perform differently, especially Dyneema, when you're pulling that slowly. I'm hoping to demonstrate the difference in strength that you would get slow pulling it versus medium versus drop tests. We have tightened the crap out of these pulleys. We believe we can get over 20K in now. Next attempt. It's sad to keep doing it. Why does the belt look like that? Oh shit. Yeah. What? That broke right there. 11.7, so we're not making very much progress. Wow, that's 1,000 pounds of force on that right now. Why did that get lifted up? Did you know if you look backwards, everything's super clear? In order to pull down on the top, it's pulling the thing at the bottom up. We're gonna fasten that a little bit tighter, maybe add an L bracket, and we'll be right back. Welcome to tomorrow. We added braces. We made it visible, so you can actually see what's going on. Since this is not our forever machine, we just have brackets here and some brackets here. And we tightened the crap out of these. And now we can actually see what's going on here. So let me stand behind my shield. Safety first.
That was anticlimactic.
Oh, we're at, well, 12.8, what happened?
Something's spinning again.
Hold on, we're holding 11K in right now. We should, okay. So it works until it doesn't. So we're getting to 12 kilonewtons and it's loose now. But this slips on the screw after that much force. The rest of it's solid. It's anticlimactic. I was really hoping that would go boom to be more exciting, but I definitely like doing things in CAD, right? Cardboard and duct tape. I like physically touching things and building them to where we understand just that user interface between you and the machine. And I think we learned a lot doing that. If you want to actually see a real CAD file of what we're currently working on, go to slacksnap.com. And we're trying to build this machine to not be $40, $50, or $100,000, because that's pretty much what they cost if you're going to have about a 5-foot screw, which is about that tall. That's so much money. And I don't think it needs to cost that much money. And I want to be able to plug it into 120 volt power. I don't want 220 volt. I don't want a forklift to be able to move the damn thing. And so I want this to be more usable for people who are like me, a dude in their garage, or a small manufacturer trying to just, there are so many small manufacturers who make stuff and don't test it. Just saying. I'd love to make that more accessible to everybody. So if we can make one for ourselves, then I'm hoping that we can make another one, or 3, 4, 5, or 6, if you guys are interested in having those. Go to slacksnap.com, you'll see what our mission is, and you'll see what we're aiming to do with that machine. And we got a CAD file that you can take for a spin. Now, if you are interested in helping us do the software for this, we are hiring a software engineer, and we have the application below. If you are interested in potentially purchasing a machine or wondering what it takes to be able to break stuff like I do on this channel, please fill out the Google form on slacksnap.com. We will understand what your needs are before we get too deep into the one that I think is going to best fit my needs, which I think is more universal for the most people. This is why I chose to go with the specs we have so far. And then in the next video, you will see us brake testing an aluminum version that's going to be version 2, but we're going to build it in a way that hopefully does actually go boom. Thanks for watching. Cheers.